Do you feel the vibes?
Okay, so having done, right, limits using a graph and using a table of values, we're going to see how we can approach the same sort of problems algebraically. So here are the properties of limits. If you have the limit as x approaches c of k, so first of all, whatever is in here after the limit, that is your function, right? So here, if it's the limit of k, that means your function right now is k. So why don't we take a look at what that looks like, for example. So y equals k is like, y equals any constant. Suppose you have y equals, 3. Okay? And this is some value c. Well, if y equals 3, then, y equals 3 every single point, on the interval, right? So as you're approaching any value, what y value is your graph approaching? Always that same value, right? So the limit as x approaches c of k is just k, right? So if you take this example, the limit as x approaches 2 of 3, you have the function y equals 3, and the limit is always going to be that same number because the graph is always approaching that same number. Now, how about if you have the limit as x approaches c of x? This time your function is y equals x. And y equals x, we know exactly what that looks like, right? That's just the identity function is what we call it. And as x approaches, let's say 2, where is y approaching? 2. And as x approaches negative 53, y is approaching negative 53. And here as x approaches 3, the limit will be 3. All right, so those are like clear as day. Now, those are the building blocks, and you can basically break down any function into a constant and an identity function, okay? So if you have, let's say, two functions, if you have f of x and g of x, and suppose the limit of f of x is L, as x approaches c, and then the limit of g of x is m, okay? So as x approaches c, one function has a limit of L, one function has a limit of m. If you add the functions, the limits will add. If you subtract the functions, the limits will subtract. Multiply, they'll multiply, and so on, right? All of these, and then if you raise it to an exponent, it'll be the same. So for example, if I have the limit as x approaches 3 of x, we said was 3, right? We said the limit was 3. Now, if I take x and if I square it, then the limit will also square and it'll be a 9, all right? That's what we're talking about. Okay, so using that, let's take the limits of the following. So here we have x approaches 2, the limit as x approaches 2 of 3. What will that be? 3. The limit as x approaches root 2 of e. Now, e is also a constant. It's just 2.718, blah, 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 right? So this will just be e, okay? Because whether it's like 3 or 2.57 or e, it's the same. Okay, now, what if you have more complex functions? If you have polynomial functions, all right? Remember, what is the domain of all polynomial functions? All real numbers, right? So if p of x is a polynomial function, if you want to find the limit as x approaches c, then you just directly substitute c in there, okay? So use direct substitution. If you have a rational function, you do the same. You find, if you have p of x over q of x, you just do direct substitution as well. And this works as long as you don't get 0 in the denominator. So here we go. You want to find the limit as x approaches 2 of this function. Now on yesterday's homework, we had to graph this thing and we had to see it. But today, all we're going to do is we're going to plug the 2 into each of the x's. Now, here we go. As soon as when you have a limit, as soon as you substitute this value into the function, that limit symbol will have to drop. Okay, so this will be just 2 minus 3 over 2 times 2 squared minus 2 minus 15. So this is negative 1 over negative 9, 1 over 9. And sure enough, just like when we did, number 41 on the homework, right? You'll see that this will just level off, or, this will approach 1 over 9. Okay, this one here. This is technically not a polynomial function, but it also works with direct substitution. So let's put negative 1 in there, and you're going to get the square root of negative 1 plus 3, root 2. That's good enough. Okay, so you can evaluate the limit using direct substitution as long as you get a defined value. Okay, cool. Okay, here, the limit as x approaches negative 8 of this. Okay, so that doesn't work, right? So that's D and E. Okay, and if you think about it, right, this function starts at negative 6, and then, we're looking for the limit at negative 8. The function isn't even, defined there. Okay, it's like barren country over there. All right, here we go. The limit as x approaches a of this, well, now just direct substitution with a. So 2a squared. Sorry, I just forgot if I did. I had to do some. Okay, I'm good. Plus 3. Okay, sorry, I had to put something away from my desk. I just remembered, but I think I put it away. Okay, all right, I didn't forget how to do the problem. Okay, all right, now everything came up, nice and peachy over here, right? However, there are some functions, clearly, right, you can't just go plugging in any number into any function because you're going to run into undefined territory, okay? When direct substitution results in 0 over 0, we call that indeterminate form. It's indeterminate because when it's 0, okay, when you have a number divided by 0, like 3 over 0, as the denominator approaches 0, yes, that will be infinity. But when it's 0 over 0, it's indeterminate, meaning you can't really ascertain. You need a little bit more information, right? So in such a case, you have to use other methods to determine the limits. So when you get 0 over 0, actually, when you do some more simplifying, it is possible that the limit actually exists, which means it converges, right? Or it'll diverge into positive or negative infinity. So let's take a look at this one. When you get 0 over 0, there are several methods that you can use to simplify your function. The first of those methods is factoring. So let's factor this one. Ooh, we have a cubic term with 4 terms. What do we do? Grouping, everybody's favorite. Okay, now, actually, you know what? I kind of got ahead of the game here. So when you plug in negative 2 into this function, sorry, I got ahead of myself. When you plug in negative 2, in the numerator, you actually get 0. And in the denominator, you also get 0, right? So so you get negative 8 minus 12 plus 8 minus 12 over negative 2 plus 2, which is 0 over 0, plus 12, right? Which is 0 over 0. So that's indeterminate form. That tells you that you have to do something else, okay? So we are going to factor this. Now, we're going to factor by grouping. If you're going to work on this function, simplify this function, As long as you are simplifying the function, that limit symbol has to come along with the function. So for example, this is going to be the limit as x approaches 2 of, let's see what we're going to factor. We're going to factor out an x squared, x minus 3. Huh? Oh, okay, I'll fix it. Minus 4, x minus 3 over x plus 2. No, I said you couldn't put the limit sign when you substituted the number. But as long as you're simplifying, you have to take the limit with you. So here we go. So this is the limit as x approaches negative 2 of x squared minus 4, x minus 3 over x plus 2. This is the limit as x approaches negative 2, x plus 2, x minus 2, x minus 3. Okay, at this stage, the x plus 2's will go away. So I have that this is the limit as x approaches, let me write it down here. As x approaches negative 2 of x minus 2, x minus 3. Do you see how the limit symbol came along every step of the way? If you don't have that, it will be points off. I am telling you right now. So right now, okay, the problem that was giving us 0 over 0 was the denominator, right? That was the problem. We just removed it. Now we can directly substitute negative 2 into this. At this stage, the limit drops. So now I have negative 2 minus 2, negative 2 minus 3, and that will be 20. So the limit of this is 20. Okay, so as x approaches negative 2, the y values are approaching 20 from both sides. Okay?
You don't have to do the first step, or just...
No. I mean, you should to test, right? Right, right. So this one, for example, will be 0 over 0. So you have to test it. So this is the limit as x approaches 6. Let's factor this. We're going to get x minus 1, x minus 6 over 3x plus 7, x minus 6. And this goes away. So this is the limit as x approaches 6. So this is 5. Now we're going to plug it in, right? So 6 minus 1 is 5 over 25, which is 1/5. Okay? All right. The next type of problem is when you have a square root. So take a look at this one. This is the limit as x approaches 25. When I plug in 25 into the numerator, I get 0. Into the denominator, I get root 25, 5 minus 5, also 0. 0 over 0. So I have to simplify this as well, right? The way you get rid of the situation here that gives you 0 over 0 is by rationalizing. Wherever you have the root, right? Root minus something or root plus something, that's where you have to multiply by the conjugate of it. So if you have root x minus 5, what's the conjugate of it? You have to multiply by root x plus 5. Now, this isn't a numerator-denominator issue. It could very well have happened that the root x minus 5 was in the numerator and you still would have to do the same thing. Now, take a look. This is going to be the limit as x approaches 25 of, okay, I know you have the urge to like multiply that numerator out. Resist that urge for a minute. We're just going to leave it like this. In the denominator, it's a minus b, a plus b. Square the first one, you get x, minus Square the second one, you get 25. This should have been a 25 up here. And now look at what happens. Magically, these two will cancel each other out, right? That's how the problem is like built. That's why you had that situation. So now all this is the limit as x approaches 25, root x plus 5. Now I can plug in the 25. And I get 10. Okay? So you see here, limit symbol, and then the limit symbol drops. Cool? All right. Look at this one. You plug in a 0 in the numerator. You get 2 minus 2 over 0. So that's 0 over 0. Okay, we have to do complex conjugate. I'm sorry, not complex, but the conjugate of this. So we're going to multiply by 2 plus the square root. 2 plus the square root. Okay, usually students forget to multiply the denominator, or like they only, I don't know, don't do that. Okay, in the numerator I have a minus b, a plus b. Square the first term, 4, minus square the second term, you just get x plus 4. Don't forget the parentheses. Over x times 2 plus x plus 4. Don't multiply that out. So, what's this going to give me here? So this is going to be 4 minus x minus 4, right? So this is the limit as x approaches 0. In the numerator, what do I have left? Negative x. In the denominator, I have x times this thing. Okay? So now, the x's go away. So I have the limit as x approaches 0, negative 1 over this. Now I try plugging in the 0. I will not get 0 over 0 anymore. So I get negative 1 over 2 plus 0 plus 4. That's negative 1 over 2 plus 2, 4. Okay? So you see how we solved that problem. Okay, what if you have to find a limit at infinity? Right? Remember, whenever you're dealing with, x approaches infinity, right? You always just look at the term with the highest degree. Remember? So, if you have like a complicated function, if f of x is like 3x to the 7 minus 2x to the 4 plus 2x minus 3, right? As x approaches infinity, none of the last terms matter. The only thing that matters is 3x to the 7. So as x approaches infinity, this is just a power function with an odd exponent, right? And if you have a power function with an odd exponent, this is what the graph looks like. Now, if instead of that, you had something that started with a 6, then everything else is negligible. You just have 3x to the 6. Then that reduces to a power function where n is even, right? And so if I have an odd exponent, I know that, it goes up to the infinities to the right, down to the left, and so on. So that's all I need to do. So take a look at this. Let's evaluate this limit as x approaches infinity. So as x approaches infinity, the only thing I look at is this term right here. Okay? So that's an even exponent. That means both ends will face in the same direction. As x approaches positive infinity, does this graph go up or down? Up to positive infinity. So the limit will just be infinity. That's all. There is no work to show for these. You either get it right or you don't. Yeah. No, well, yes, Diani as well. Sorry. Yep. I was going to say that next and then, yeah.
How do you know if they're both pointing up to the first is positive?
Huh?
Are they both pointing like up
Mhm.
as the first is positive?
Yeah, because the coefficient is positive. Okay, next. Negative, okay, here. As x approaches negative infinity of this, so this is the leading term. And so now, okay, this is a negative, and if x is approaching negative infinity, then it's going to be negative, negative, positive. Okay, so this is going to go up to positive infinity.
Is it just like the regular graph that was in all exponents?
Mhm.
Mhm.
Here we go. Leading term is which one? 4x to the 5. As x approaches negative infinity, who says the answer to this is positive infinity? Who says it's negative infinity? Negative infinity for sure. Here we go. Right? 4 minus x squared, right? So negative infinity as well. Okay. Yep. Okay, what if you have a reciprocal function at infinity? So when you have a reciprocal function like this, 1 over x, you all know that at the infinities, these things just go, and they follow a horizontal asymptote, right? So at infinity, again, we have to look at the leading term, but this time we have a leading term in the numerator and a leading term in the denominator. So we've done this a billion times, right? So if the degree of the numerator is less than the degree of the denominator, then it will be 0, right? So for example, the limit as x approaches infinity of this. So I compare the degree here and here, right? Let's just write this out. This will be the same as the limit as x approaches infinity, x squared over x cubed, which will be the same as the limit as x approaches infinity, 1 over x, okay? And so clearly as x approaches infinity, this will be 0. Do I want you to write all that stuff out? No. You should just go from here to 0. There shouldn't really be any work to show for this. If the numerators are equal to each other, then you compare the exponents. Okay, so negative 2x cubed over 6x cubed. Okay. And then if the numerator has a higher degree, then you have to just simplify it. So it's going to be plus or minus, right? Infinity. So x to the 5, negative x cubed. This will be what? It's negative x squared, so it'll go to negative infinity. So x to the 5 over negative x cubed. Right? It reduces to negative x squared, right? Right? So if it's negative x squared and if this x is infinity, then it's going to go down to negative infinity. Okay, so what about this one? You have a higher exponent in the numerator, in the denominator, so it's going to be 0. Okay, what about the next one? Negative, it's negative x, which will be negative infinity. Here, 7 over 2. All right, let's do piecewise functions, and then that's where we'll stop. Yep. Huh? Okay. So let's take a look at piecewise functions. Last night in the homework, I had you graph the piecewise functions so you guys can figure out what the limits were. Okay? Today, we're going to do it algebraically. So, the limit as x approaches 3 of this, right? So now, you just have to look at what's happening as x approaches 3. So what you do is the following. We've done this before as well. You take 3 and you put it in here, right? What value does that give you? Okay, so here's how you're gonna write it out though. So you're gonna say the limit. Oh, you know what? I was gonna fix this. So this should have said, this is written wrong. So it's not written wrong. The notation is wrong. This should have said f of x equal to, and then we had to find the limit of f of x. So the limit of f of x as x approaches 3 from the negative side. Okay? So now this is x is less than 3. It's to the left of 3. So as x approaches 3 from the negative side, we plug it in. 2 times 3 plus 7 equals 13. Next, you say the limit of f of x as x approaches 3 from the positive side is 3 squared minus 1, 8. Okay? So you say the limit of f of x as x approaches 3 from the negative side. Where are you going? Oh, okay. All right. So the limit as x approaches 3 from the negative side is not equal to the limit of f of x as x approaches 3 from the positive side. Therefore, the limit of f of x as x approaches 3 is dne. Right? Because what have I always said? Is it ever about the final answer? No, it's about the why. It's about the process, right? It's about the justification. You've got to justify. And yes, you have to show me all of this. Yep. Yes, that's the important part. No, I mean, I can see it, but you still have to tell me. Right? Okay. So, here we go. Limit, so this too, I was going to say f of x is equal to, okay, so the limit of f of x as x approaches negative 1 from the minus side is negative 1 squared plus 2, 3. The limit of f of x as x approaches negative 1 from the plus side is also 3. Now, I can still see that there are 3, but we still have to write that step. You say, since the limit of f of x as x approaches 3 from the negative side is equal to the limit of f of x as x approaches 3 from the positive side, okay, the limit of f of x, okay, as x approaches 3, my pen stopped working. The limit of f of x as x approaches 3 is 3. Negative 1 is, oh, these are negatives. Negative 1. Okay, negative 1s. All right? Okay, so we'll stop here, and I've split up the homework so you can do it with, all this information.
Press start.